Challenge day number 1. Let's take a look at some problems. All right, this first one says, in the figure, the two concentric circles, what do they mean by concentric? They mean that the smaller circle and the bigger circle both use the same center point A. So it's kind of like a target, if you will. And they have radii of 6 and 14. So radius of 6 we could draw in here, radius of 14 we could draw in over here, but we're not going to draw them there yet. Chord BF of the larger circle intersects the small circle at C and E, as shown in the diagram here. CE, which represents a chord in the smaller circle, has a length of 8, and AD is perpendicular to BF. So if that's perpendicular, that means we get some 90-degree angles. And we can draw in, not in yellow, we can draw in a couple 90-degree angles here. Now, we are tasked with finding two things in this problem. How long is it from A to D, and how long is it from B to F? All right. Now, my first recommendation would be we might want to draw in some radii, right? So let's draw in, let's first start with the smaller radius. Let's go from A to C here. And so that has a radius of 6. Now, AD is our first unknown thing here, so I'm going to pop an X right here where AD is at. And so it would be really helpful if we knew what CD was, but we were told what CE was, that it was 8 altogether. Now, one of the properties that we talked about in video 2 was if we had a chord in a circle and we looked at the shortest possible distance to that chord to the center of the circle, and the shortest possible distance was a perpendicular distance, which we have, then this AD, this shortest distance, will bisect the chord. So this chord of 8 gets bisected into 4 and 4. And so we can now use the Pythagorean theorem in this right triangle to solve for AD. So x squared plus 4 squared equals 6 squared. And so 4 squared is 16, 6 squared is 36. Subtract our 16 over to the 36 and get 20. Square root both sides, and the square root of 20 breaks down into the square root of 4 and the square root of 5. And the square root of 4 gives us a lovely 2, and the root 5 has to stay. So there's the length of AD, 2 root 5. Now, for BF, we know at least BF has a length of 8, because from C to E is 8. We just need to figure out those two pieces. Now, one thing you might consider doing is putting in a new variable and saying, well, let's call this piece Y, and let's draw in a new radius. Let's say now over here from A to F, that radius has a length of 14. Now, you could set up the Pythagorean theorem with this new right triangle we've established, but I will tell you right now, and so this x, remember x here is that 2 root 5. So we do know the length from A to D now, and the only unknown is this y. So we could set up the Pythagorean theorem here and solve for y. But I'm going to give you a little bit of a heads up warning here, that if you set up the Pythagorean theorem to look like this, wow, that's a crazy plus, there we go. If you set up the Pythagorean theorem to do this, it ends up being a quadratic, which you're going to have to solve a quadratic, and it doesn't factor, so then you're going to have to use the quadratic formula. And it's just kind of a big pain in the butt process, and there is an easier way to do this. So I'm not saying that this is a wrong way of setting up the Pythagorean theorem, but I will advise you that there's an easier way. And so let me show you the easier way. The easier way is this. Instead of figuring out how long it is from E to F, the main thing we want to try to do, let me backpedal here just a little bit, we were trying to find the length of this entire big chord BF, right? But if you notice, AD is that shortest perpendicular distance, not only to CE, but also to BF. So that means BF gets bisected, so that from B to D is the same length from D to F. And so if we could figure out how long each of those two little pieces are, then we could double it and we'd have the whole chord. So my advice is not to call EF its own variable, but rather let's call from D to F its own variable. And so for right now, we're basically ignoring this 4. We used the 4 to help us solve for AD, but now we're just going to kind of ignore that that 4 even exists. Okay? So from D to F, we're going to call Y. From B to D is the same thing. And so really, once we figure out what Y is, we can double it or add it to itself, and then we'll have the whole BF. And this will be a much easier setup to solve. All right, so let me erase this little bit of work over here. And now let's set up the new Pythagorean theorem with this. So this is going to be 2 root 5 squared plus y squared. Remember, y is that whole df piece, equals 14 squared. And so 2 root 5 originally came from the square root of 20. So if I unsimplify my 2 root 5 back to a square root of 20 and I square a square root of 20, I'm going to get 20. So 20 plus y squared equals 14 squared, which is 196. Subtract the 20 over to the 196 and we get 176. Square root that. And you might have to play around with the numbers here, but this is 16 times 11 is 176, which makes that equal to 4 root 11. Now, 4 root 11 is not our final answer. 4 root 11 is half of the answer, because from B to D is another 4 root 11. So add those pieces together, and altogether BF has a length of 8 root 11. All right, there's the first problem. The second problem, 2 concentric circles. Oh, so this kind of starts off the same way as the first problem. So it'd be nice if we had a picture here. So let's draw 2 concentric circles. Let's draw one circle inside the other in such a way that they approximately have the same center point there. All right. Let's see, would it be helpful if one was different color than the other? Sure, why not? And they give us the radii, 4 and 8, just like they did in the first problem. A segment tangent to the smaller circle is a chord of the larger circle. What is the length of the segment? So this almost looks like the first problem, except instead of the chord, this big chord also being a chord inside the smaller circle, they're saying we don't want this to be a chord inside the smaller circle, we want it to be tangent to the smaller circle. So what that means, let me kind of get what's going on. So here's what the first problem looked like. No, let me get a different color here. Here's what the first problem had us consider, right? But they said we don't want this to be a chord, we want it to be tangent. So we're going to have to push it down until it's just touching the little circle at one point, and then we're going to have to shorten these ends up here. There we go, like this. So notice, to the small circle, this segment is tangent, but this segment is a chord of the bigger circle. They want to know what is the length of that tangent segment, or of the chord of the bigger circle. All right. So we're going to need to draw in some more things. So it would be helpful if maybe we drew in a radius. And what happens when a radius meets up with a tangent? Well, it is perpendicular. So we can make some 90-degree angles here. And we also know what the length of that piece is, because that's the radius of our smaller circle. So this has a length of 4. Now, another helpful segment to draw in would maybe be from the center all the way to the edge of the chord, of the tangent segment, because that represents the radius of the bigger circle, which is 8. And so now we can figure out how long this piece is in the right triangle. Well, how long is that piece compared to the whole thing? It's going to end up being half. Why is it half? Because we have this shortest possible distance from the center of the circle to a chord, because it's perpendicular thanks to the tangent relationship. And so the overall chord is bisected. So these two pieces will be the same. We can call these both x or whatever variable you want. So now we can do the Pythagorean theorem. We'll have x squared plus 4 squared equals 8 squared. X squared plus 16 equals 64. subtract the 16 over to the 64, and we'll end up with, what, 48? And square root that. The fastest way to break down 48 would be 16 times 3, which gives us 4 root 3. Now, keep in mind, that's not the length of the whole segment. That is the length of half the segment, because this piece is 4 root 3, and this piece is 4 root 3. So altogether, the length of the segment is 8 root 3. And there is our final answer for number 2. So, quicker problem. Very similar to the first one. All right, here's the third problem. Solve for x. So here's x. Notice x is one of those things where it is the shortest possible distance to this chord of length 20. How do I know it's the shortest possible distance? Because of the 90-degree angle. It is perpendicular. So if you want, you could draw in another 90-degree angle here. And we know that this piece and this piece will be the same, which means they have to be matching tens. Now, down here, we can see a very similar setup, that we have this 5. It is also perpendicular to this chord of 24, and the 24 is going to be bisected into a pair of 12s. Now, my first question to really ask here is, why can't we just say that x is 5? And we can't say that x is 5 because these two chords are not the same length, right? If this was 20 and this was 20, well, then these would also have to be matching 5s. But since this 20 is different than the 24, then this x will be different than the 5. Now, one question I would then pose to you in class would be, well, should x be bigger or smaller than 5? If you think about, if this chord up here is 20 and this is 24, then would x have to be bigger or smaller than 5? And I'll have you kind of think about that one, chew that one up in your brain a little bit, and then we'll actually solve for what x is, and we'll see if you were correct in your hypothesis, if x was going to be bigger or smaller than 5. Now, for this problem, again, we're going to have to draw in a radius. Typically, that's what we're going to find we're going to have to do many times. So if I drew in a radius here, right, and then I've got this lovely right triangle that I could use the Pythagorean theorem for. Except I run into a problem up here, is because I don't know what x is, and I don't know what the radius is. They never told me that information like they did in the last two problems. So I can't do the Pythagorean theorem yet. So where else could I go at in the problem? Well, I could draw in another radius down here as well. And now notice that in this right triangle, I have more information than I had in my first right triangle. So this is a 5, 12, and this is a Pythagorean triple. This is a 5, 12, 13. If you didn't recognize the triple, you're just going to have to do the Pythagorean theorem. So this is a radius of 13, which now means we can move it over and say, well, this radius is also 13 as well. Okay, so now we can do the Pythagorean theorem, and this is not going to be a triple in this other one here, but this will be x squared plus 10 squared equals 13 squared. X squared plus 100 equals 169. Subtract the 100 over to the 169 to get 69. Take the square root of that, and honestly, the square root of 69 does not simplify. And so x is the square root of 69. All right. Problem 4. Now this one is going to look pretty similar to the very last question of video 1. All right. So the circle is inscribed, which means it's drawn inside the circle, or drawn inside the triangle in such a way that it's bumping up against all three sides of the triangle at those 3 points that I just showed you there. Determine the radius of the circle. All right. So I could draw in the center of the circle. And so some helpful segments I could draw in would be to the 3 tangent points. So radius comes up here, hits that tangent point. That means that it creates some 90-degree angles. When the radius comes over here and touches side AC, it's going to make some 90-degree angles. and when the radius comes down here and touches side AB at the tangent point. Then we get some more 90-degree angles. So each one of these represents the radius, which we're trying to figure out. All right, so now the key to unlocking this problem was realizing that this particular quadrilateral, it currently has 1, 2, 3 90-degree angles. And it's because the triangle we started with was a right triangle, right? We didn't know that that would have been a right angle had they not told us that. That really helps unlock the problem in saying that this fourth angle must be a 90-degree angle as well. And so now we've got a quadrilateral with 4 right angles. So this thing's either a rectangle or a square. But if you consider that this is a radius and this is a radius, well, if these adjacent sides are congruent, then this isn't just a rectangle, it's really a square. Which means that this piece has a length of r, and this piece has a length of r. And that also verifies for us the party hat theorem, that these two pieces outside of here must be the same. And so now we get to look at other party hats. There are 3 party hats altogether in this problem. And then we're going to get to work with the party hat theorem. So this is R, and so if all the way from A to C was 5, and we're saying that from here to here is R, well then how much is left over from A up to this tangent point? Well, this would be the whole thing 5 minus whatever that other little piece was, R. And so this party hat piece is also 5 minus R. All right? And so then, well, how long is it from here to here? Well, if this piece is 5 minus R, well, then this piece is going to be the whole thing, 13, minus what that little part over there was, 5 minus R. But notice I'm putting that in parentheses. So really, this is 13 minus 5, and then we're subtracting a negative R, so it's really going to be a plus R. 13 minus 5 is 8, and then it's going to be plus R, 8 plus R. All right, which means this party hat is 8 plus R. Okay? Now, the one thing that we didn't do, which I probably should have done initially, was overall, this is a 5 something 13 right triangle. And this follows a Pythagorean triple, which means this whole side has a length of 12. It's a 5, 12, 13 right triangle. And so now if we look at the two pieces that make up this 12, that's this piece, this 8 plus R, and this piece, R. So when I add R to the 8 plus R, that's got to give me a length of 12. So 12 is equal to R plus this 8 plus R piece. So 12 is equal to 2R plus 8. Subtract the 8 over to the 12 to get 4 equals 2R. And R, the inscribed circle's radius, is 2. So there is problem number 4. Number 5, calculate the length of segment DC. So where's DC at? DC is right here. All right, be sure you can explain why you were allowed to do the math you did along the way. Now, this is going to use some previous chapter information when we did similar triangles. So let's see, what do we got here? Well, notice here we've got some party hats. So we know this is a party hat because notice this is perpendicular, this is perpendicular. These are both two tangent pieces. So we know the length from E to C must be 3. And same thing on the other side here. From D to E is a party hat with B to E. And so we can also put an X up here. So the length of DC is whatever X plus 3 is. But we got to figure out what the X is. So now to use some of our old chapter stuff here. And so what we're going to do is we're going to focus on, and it doesn't really matter which triangle, but I'll use the original triangle here. So this right triangle and this right triangle. So notice they both have matching 90-degree angles. and they also have matching vertical angles. So these two triangles are similar to each other by angle-angle similarity. So this is why I had this part in here. So because we have similar triangles, then the sides of those similar triangles are proportional. So we get to set up a proportion now. So the x in this triangle is going to match up to the 3 in the smaller right triangle, and that'll be equal to the 3 over here, the radius of the bigger circle, over the radius of the smaller circle 2. So now cross multiply, and x is 9/2, or 4.5, or 4.5, however you want to give it there. So we now know that this is 4.5, 4.5. So 4.5 plus 3, DC has a length of 7.5, or 7.5, or 15 halves. So this one wasn't that terrible, but it required you to think back to last chapter. And the last problem. The figure shows two semicircles with centers at P and M. The semicircles are tangent to each other at point B, so this semicircle touches this semicircle at exactly one point. They don't cut through each other. And DE is tangent to both semicircles at E and at point F. It's tangent. Again, be sure you can explain why you were allowed to do the math you did along the way. So again, we're going to end up doing some older stuff here. So if PB is equal to 6 and BC is equal to 6, so notice that this is the diameter of the smaller semicircle, so that makes this piece 3 and that piece 3. Then solve for ED. So ED is this piece right here, that first kind of tangent piece. I'm going to put an X. Really ugly looking X. Let's try that again. Let's put an X. There we go. Okay. All right. So what are we going to do here? I don't know. What do you guys think? I don't know. We always tend to draw in radii, right? So we could draw in this radius from E to M. We were told that this was tangent to the circle, so we know we get to draw in a 90-degree angle right there. And also if we draw in the other radius from P to F, that it was tangent to DF, so we get to put a 90-degree angle up here. Now, notice PB, that's the radius of the larger semicircle. And this piece I just drew in here is a radius, so it has a length of 6. Likewise, that first radius we drew in is going to have a length of 3. Okay? So I'm seeing already, kind of in the last problem, some similar triangles. I see this right triangle, and I see this right triangle. Now, both right triangles have 90-degree angles, but what other angle do they also have in common? They also share a reflexive angle, angle D, right? Because in the big right triangle, we use angle D fully, and in the small right triangle, we use angle D fully. So I could make a statement that triangle FPD is similar to triangle EMD by angle-angle similarity, which means if the triangles are similar, then their sides are proportional. And so that's what's going to help us figure out how long this piece is for x. All right, so we just now need to figure out, well, where are those sides that we can set up there? Okay. So how about we come down here and let's call this piece. Do we want to call that piece something? Yeah, let's call this piece. Let's call from C to D. Let's call this piece, if it'll let me write, there we go. Let's call it Y. The one ratio that we know we get to use in this problem is the radius to the radius. We know that there's a 3 to 6 ratio here, aka a 1 to 2 ratio, right? And so what we can now do is I'm going to focus on the hypotenuses here. And so what is the hypotenuse of my smaller right triangle, well, that would be this 3 piece plus this y piece. So that's y plus 3. And then what is the hypotenuse of the bigger right triangle? Well, it's this 6, and really this 3 and 3, which together make a 6, and this y. So y plus 6 is y plus 12. And so now, when we cross multiply and solve here, we're going to have to distribute the 3 to the y plus 12, and we're going to have to distribute the 6 to the y plus 3. So we'll get 3y plus 36 equals 6y plus 18. Subtract the 3y over to the 6y and be left with 3y. Subtract the 18 over to the 36 and get 18. We know that this y piece is equal to 6. And so now we can use some Pythagorean theorem, because in this small right triangle we now officially know 2 full sides. We know this side is 3, and we know this full hypotenuse is 3 plus this 6. It has got a length of 9, and now we can set up the Pythagorean theorem. So let's go x squared plus 3 squared equals 9 squared. X squared, ooh, crazy squared, x squared plus 9 equals 81. Subtract the 9 over to the 81 and end up with 72. Square root that. Best breakaway would be 36 times 2 is 72. And the square root of 36 is 6 with our root 2. So the length from D to E is 6 root 2. And there's the last problem.